particular topic, force, is for class 10th students particularly. We'll be learning about force. Remember guys, force is that physical quantity which does four things. Either it can start a body at rest, that means it can bring a body into motion, or it can bring a body which is already into motion to rest. It can also change the direction of a moving body, or it can change the direction of a moving body. These are the four fundamental things force can do. This is particular thing what force can do we already learned in class 9th also. Over here, force can bring translatory motion to a body. When I say translatory motion, it means a body moves along a straight line and changes its position with respect to time. That's what translatory motion. Or it can rotate a body, that means it can provide rotational motion to a given body. When I say rotational motion, that means body is pivoted at one end. Let's say this is a key ring which is attached to a nail. If I apply force to this particular key chain, this is the point of application of my force. The key chain is not going to move on a straight line path, but it's going to rotate around this pivoted point. Now, this particular distance or the perpendicular distance from this fixed point I took as D. So the direction, angle between the distance, perpendicular distance and force is 90 degree. The product of force and displacement over here, the product of force and displacement over here is known as torque. I'll be representing torque by a Greek letter tau. Over here in this chapter, we'll be learning about rotatory motion. We are not interested in translatory motion over here according to the syllabus. So the first heading under rotatory motion is torque. Torque is given as product of force and displacement. Basically, torque is force multiplied by displacement multiplied by sine of angle between force and displacement. But for sake of simplicity, we'll be taking only those cases where the angle between force and displacement is 90. That means the formula for torque which we'll be using is force into displacement, because sine 90 is 1. SI unit of torque will be Newton meter, because the SI unit of force is Newton, SI unit of distance is meter. Care should be taken not to inverse them, not to write M and then N, because that stands for millinewton. This is the first formula we'll be using in this chapter. Now please remember, if we apply torque to a given body, that means the body starts rotating. This effect is known as torque. Rotation can be of two types. The body can either move in anti-clockwise manner, that means like this, or it can move in a clockwise manner, as you very well know, the direction of movement, what is clockwise. If direction of body is anti-clockwise, torque is taken as positive, and if direction of torque is clockwise, torque is taken negative. This is sign convention we'll be using in this particular chapter. Now let's move to the next heading, which is coupling. Over here, we are applying two forces rather than one. If you see over here, like while moving a tap, closing or opening a tap, we apply forces, equal and opposite forces. Over here, equal and opposite forces when applied to this particular bar AB, it starts rotating. As you see over here, it will start rotating in a clockwise manner. Now if I find out torque about a fixed point O, let's say this is your fixed point. First I'll be finding out torque about OB in this part. For this part, my clockwise torque will be force, which is F, multiplied by perpendicular distance, which is d1, obviously SI unit Newton meter. If I find out clockwise torque about O from point A, which is again clockwise if you see, will be F multiplied by d2. I have not written negative sign over here because I have already mentioned clockwise. If I wouldn't have mentioned clockwise over here, then I need to put a minus sign over here. Total torque clockwise. Total torque clockwise. Since both are in same direction, so total torque gets added up. If I add them up, F comes out to be common. In bracket, I get d1 plus d2, which is the total distance between A and B. So force multiplied by total distance AB, Newton meter, becomes your total torque. So remember, couple, we have two forces equal and opposite. And for finding out couple or moment of couple, we need to find out the product of force multiplied, either force. It can be this force or this force multiplied by perpendicular distance between the forces. Now a question is there. What's the difference between torque and couple if both rotate the body? In couple, remember, we have two forces which we apply. Torque also has got two forces, but one is your applicable force and the other force is applied by this fixed point. This reactionary force is not taken over here. Reason being, its perpendicular distance from axis of rotation is 0. So that effect is neutralized. This is the difference between torque and couple. Next heading, students, is equilibrium. Equilibrium is of two types, static and dynamic, as we see over here. A body is said to be in static equilibrium if the total sum of forces acting on the body is 0. Let me explain it to you with an example. Let's say a book is placed on a table over here. The weight of the book is acting downwards. That means it's putting its weight on the table. Table balances it by giving it an external reactionary force, as you see capital R over here. Let's say we give a small push to the book, F, capital F, in the forward direction, but the book still doesn't move because there is a small frictional force acting opposite to the direction of applied force. So over here, if I ask you how many forces are acting, we say capital R, reactionary force, upwards, capital W, weight of the book, downwards, capital F, applicable force in the forward direction, and small f, frictional force in the backward direction. But then too, the book is as such, that means it is still. It clearly means the sum of all these forces acting on the book is 0. This particular case is case of static equilibrium. Equilibrium is of second type, which is called dynamic equilibrium. Over here, if a body is moving, the body can move in a translatory motion or a rotatory motion, but it does not change its speed or velocity. In other words, the external parameters, the speed of the body is same. We say body is in dynamic equilibrium. A raindrop, when it falls with a constant velocity, which we call terminal velocity. We will be dealing with this later on. Or a ball which is moving inside a well, inside water, moves with a constant velocity, falls with a constant velocity. These are examples of dynamic equilibrium. Or if you take a keychain in your finger and start rotating it with a constant speed, that's also an example of dynamic equilibrium. So the basic difference between static and dynamic is, over here the sum of forces acting on the body is 0. Over here the sum of forces as well as the total torque, remember, acting on the body becomes 0. That's the basic difference between static and dynamic equilibrium. Students, next heading which we'll be dealing is principle of moments. In this particular case, I'll be taking example of beam balance, which we have seen in shops of shopkeepers. When you go and take something, they put whatever you want to take into one pan and measure it with weights on the other pan. So let's say this is first pan on the beam balance, this is second pan on the beam balance. These are weights. It applies force F1 downwards. This is that particular thing which you want to buy. It's put on the first pan, it's applying force F2 downwards again. That particular O is pivot where it's balanced. Let's say its distance from first pan is D1 and from second pan it's D2. If you clearly see that from this fixed point, if I ask you what's clockwise torque, this F1 tries to move the pan in clockwise direction. Hence clockwise torque will be F1 into D1. I have put a negative sign just to make sure that this is anti-clockwise torque. SI unit Newton meter. Similarly, if I ask you what's anti-clockwise torque is given by F2 multiplied by D2. So F2 D2 Newton meters. This is anti-clockwise torque, this is clockwise torque. Principle of moment states that whenever a body is in balanced or equilibrium position, I repeat, whenever a body is in balanced or equilibrium position, I wrote over here total torque for balanced or equilibrium position. The condition is anti-clockwise torque should be numerically equal to clockwise torque. That means clockwise and anti-clockwise torque when added should give us 0. So clockwise torque I wrote over here as minus F1 into D1. Anti-clockwise torque I wrote as F2 into D2. Taking this over there, we get F1 D1 equals F2 D2. That this is the condition for principle of moments. I repeat, it states that for a balanced condition, anti-clockwise torque should be equal to clockwise torque. In the next part, I'll be dealing with the numericals of this chapter. Till then, please revise these derivations so that you can easily solve out the numericals. Please don't forget to like and subscribe my channel. Tomorrow we'll be dealing with the numericals of this chapter. Till then, goodbye. Thank you.